In this subsection, we're discussing matrix of linear transformation where the input space and the output space can be different. So what we have is that in the input space, x belongs to the vector space V. Tx, the image of x, belongs to the vector space W. T represents the transformation. In this case, V is an n-dimensional vector space. So it's Rn. So x can be represented in Rn, and we call this the change of coordinate into the B basis, using the B basis. So x of B is x in the B basis, and it is in the Rn space. Now, however, we have output T of x that is represented not in Rn anymore, but Rm. M is not equals to n. And therefore, T of x, and we call this the C basis for the output. This C basis is in Rm space. Now, what we also can show is this picture. On the top is x being transformed by the transformation matrix T to get Tx. The input can be represented in the B basis, xb. The output is represented in the C basis. To get from xb to the output, let's call this y, in the C basis, we multiply by m. So meaning this yc is equals to m by xb. So the question now is, what is m? Well, remember that this is a m by 1 vector. This is a m by 1 vector. This is a n. The input is a n by 1. Therefore, m is a m by n matrix. So we are trying to now figure out how to find m. So this equation shows us how do we find m. M is defined to be the columns of M. There are n of them. Is simply the transformation acting on the B basis, one column at a time. So there are n of them because these are the basis for the input, and because we need m to be in the C basis space, we convert this into the C basis. Okay, so this is the M matrix representing T relative to basis B and C. To understand why M is defined this way, you can read the above text, as well as seeing the argument in this page over here. Okay, thank you.